Now let us see the lecture number 6 of module 2. In the previous lecture, that is lecture number 5, we saw the various definitions of the various type of stabilities and the different subclassification, again with respect to the disturbance, means magnitude of disturbance, time frame, and again the quantities of interest. In this lecture, I will discuss about the transient stability of the power system, and then we will see what are the ways that we can analyze. First one is classical approach for the transient stability analysis, and the various assumptions are made in the classical approach. First one is the mechanical input to the generator remains constant, means governing system action is neglected. Means if your system here, this whatever the generators, your G, here we are giving the mechanical power, and that is coming through your turbine system, again turbine system, then governing system. So this we are assuming for that analysis period, this PM is almost constant, and that assumption is valid, because here the transient stability, our analysis is concerned up to 5 to 10 seconds. So by that time, here the governor action or prime mover action is almost negligible, because the time constant of this is very, very high. So we can ignore this. Means your mechanical power input to the generators are remain constant. Second assumption here is the mechanical damping, that is a machine damping, and the AVR action is also neglected. Means the damping of the machine, that is D, and the automatic voltage regulator action is also neglected. The synchronous machine model as a constant voltage source behind a transient reactance. Means here it is your generator. So we model this generator with some reactance here, and this is your terminal voltage. So this reactance is nothing but your X D prime. Again, as in the previous lectures, we have seen the synchronous alternator may have two types. One is your cylindrical rotor, another will be the salient rotor type of machine, where XD and XQ are different, but however in the synchronous machine it is a XS, that is a constant, and it is irrespective of the D and Q axis components. So if it is a salient, then it is your XD prime, and if it is your cylindrical rotor machine, then it will be XS. So it is your the constant voltage source EF behind this voltage behind this terminal voltage T, and this is your subtransient reactance of this alternator. Then we can model in this way. So the machine can be represented by the classical. This is also called the classical representation of the machine modeling. Also we know in the power system, all the components, they have some dynamics, and they have their equations, and their dynamics are there. For your example, your network dynamics, protection system dynamics, your governor dynamics, your mechanical inputs dynamics. So all are having the dynamics. But in this classical approach, we also ignore the network transients. Means those are neglected. Thus the static model of the network is considered. Only we have to go for the static model in this classical approach. Load also may have some dynamics. For example, your induction machine load, that will be also changing with the change of your voltage as well as the changing in your reactive power requirement. So but in this classical approach, we model load at the simple impedance or admittance form. The mechanical angle of each machine rotor coincide with the electrical phase of voltage behind the transient reactance. So these are the 5 assumptions are made in the classical analysis of the transient stability. So analysis utilizes the static equation of network and the dynamic equation of machine. As I said, here the network, just we have to take the static model, and others we have to take here the dynamics of the machine here, that is included. Let us see a generator G here, that is connected with the transformer having impedance XT, and here these blocks are basically the circuit breakers. Means we can trip this portion, we can trip this transmission lines as well, and here we have the infinite system. Normally most of the analysis people go for either single machine infinite bus system, that is called SIMB, single machine infinite bus machine system. So this is basically your infinite bus where normally this voltage angle is 0. Means again, what is the infinite bus? Why it is called infinite? Whether infinite in terms of its location, infinite in terms of its, what is the infinite term? Why? So infinite bus is a bus which is, if you are injecting power or you are extracting power from that bus, normally there should not be any change in the voltage and the frequency of that system of that bus. So this is called infinite, means you can draw effectively infinite power, which is practically not possible. But if you are drawing large power and there is no change in the voltage and the frequency of that system, then we can say that bus where we are drawing the power is known as your infinite bus. So here basically this is another system and where this bus is located. So you can draw more power here at this bus, means here practically the voltage and angle is constant, whatever the power you are taking. So we have this system, one generator, the transformer, and then we have the two lines, line X here, that is impedance is XL1, and another is here your XL2. Now this machine, as I said, in the classical model, we can represent this machine as E, and then we can have a reactance here, and this is your voltage source, that is your XD prime. So now your this bus, this system we can represent here with this one. Now this is a transformer. So this PM we have assumed constant, but this electrical power P is changing and it depends upon the system here, the angle, etc. Now for the cylindrical rotor, we can write the P. If you remember, already we have defined this P for any machines here is V1 V2 upon X sine delta, and this delta is the difference between the angle of the two buses, and that bus is the element which is XS is considered. For this case, we are just considering here one bus here and another we are talking here. So the impedance in this bus is, let's suppose here now what will be this X. Now this X component just we have to calculate. So we have to write here now our V1 in this equation is nothing but your E, because we have taken here E angle delta of this bus. So your this V1 is E and your V2 is nothing but your V, and X is the total reactance of this whole system, including your this as well. So this is your complete. So we can write now, this can be simplified, this P, that is PE, is equal to your E multiplied by your voltage, that is the infinite bus voltage, divided by the XD prime sum, means the total X here, as I said here is X, and the sine delta, basically angle here the 0, and the internal here angle is your delta. Now this XD prime will be nothing but the reactance of your generator, that is XD prime, the reactance of your transformer, here this is this, and these two lines, basically this is in series with this, and the impedance, parallel effective impedance, is series with these three. So these two are in parallel, so it is a parallel combination of the reactance of these two lines, this XL1 and XL2, this it is a parallel. So it is a total XD prime will be this, and then we can write the electrical power which is flowing out from this system. Here P can be related here, and that is basically in terms of your cylindrical rotor machine. To see the same system, if your machine is a salient rotor type of synchronous machine, then we have also derived this. Here this is your EQ prime VI. Now here EQ and the VD both are the different one, means here this EQ prime divided multiplied by your V infinite plus sum of the reactances in that line, and again here we have another component here. So this is your delta, it is a 2 delta, and already in the previous lecture I have shown that. So if your rotor round rotor case, if your V infiniting, this X and E prime are constant. E prime is nothing but, in the previous case it was E. If are constant, then we can write this PE is nothing but is a function of your simply delta, or you can say sine delta. And if you will draw, then you will find here curve of here sinusoidal here. Means we are getting some constant k sine delta. Means if your delta is changing, your the power that will be keep on changing, that's a P. So this is called your P delta curve, and at the 90 degree pi by 2, this k term will be maximum and it is called P, that is a P maximum. Means when it is degree or is 90 degree, then we can have the P maximum, means maximum power that we can flow. So the area which is just this side, it is your stable zone, this, and outside this is your unstable. Now always what will be your operating point? Let us suppose your this mechanical power, this Pm, is this axis. So your electrical, always we know for the steady operation this Pm should be equal to your P. Then here we can have your K, that is K term is here, this is your nothing but K, that is a P max, we can say P max sine delta. So this is a curve of sine delta, so this will satisfy at a point, and that is basically the intersection of this curve, this, and this curve. So this point A is your operational point, and the angle, there is a torque angle, a machine angle, that will be your delta naught here. So your machine which was here, that's I wrote E angle here, now it will be delta naught if your system is without any disturbance and it is in steady state, it is operating with this your previous case here, this is your transmission system like this. Now, and this is your delta angle where it is operating. So we can go up to slowly, if you have slowly and slowly we can increase without disturbing the system. Slowly if power is increased, then we can go up to this point, and this is normally called your steady state stability limit. But always we operate our power system much below this steady state, that is a P max value, because always you know there is a dynamics, always there is a change in the system. So if you are operating here, there may be possibility your system may be your an unstable zone, because this area is unstable and this side beyond this pi by 2, and then your system will be collapsed and it is not possible to operate. Let us see the power transfer on a transmission line. So far we have seen the power transfer including your machine, transformer and the transmission line. Here let us, we have a bus I and the bus J, and we have the angle here Vj delta Ij, and here the voltage magnitude is Vi and the angle is delta I, and this Z of this line is R plus Jx. So we can write here the Pij in this line with this formula. This is nothing. Here this Pij is nothing but your Vi, that's complex, into your Iij, that is your Vi minus Vj conjugate, divided by your Iz prime, and here basically the real of this. And if you simplify, you will get this expression. So basically it is a Z square. If your R is 0, means your line is lossless, means normally R is very small, so we can ignore compared to the X, then we can get this whole expression. R is 0, we will get this, and this is 0, so we can get this X will be cancelled, and we will get the Pij is approximately Vij Vj. Vi into Vj divided by X, reactance of this line, sine delta, or we can say this Pm sine delta. So for the line or for whole system, this formula is equally valid. Only you have to remember in this case that this delta is the angle between the two buses where these two voltages. So that's why here I write this P between two nodes. Node means two buses. Here this voltage of one bus, one voltage of another bus, divided by X between these two buses. Means there may be several. For example, here one line is this, there may be another line here, there may be some transformer here, and then another bus here. So if you are tracking, this is V1 and V2, so the whole X will be the total of these line 1, line 2 and transformer. and the angle here is the difference between angle of these two buses. So here x is the total x, and then it is your sine basically delta 2 minus delta 1, or basically here delta 1 minus delta 2, what is the direction. Means if your power is, you are calculating the power is flowing here P in this one, so it is delta 1 minus delta 2, as I explained in the previous lectures, that real power will flow from higher angle to lower angle. So this expression is equally valid, and this is the case when r is very, very small, and that can be taken as 0, then this whole expression is valid. If r is very high, then we cannot write this one, and especially for the distribution system you cannot write this. You have to take this expression, which is the original expression. Now let us see another one. This steady state stability limit, that is a Pm, that is you can say V1 V2 upon x. It is sometimes called Vm, sometimes called Pmax. So it is given in the different books here. Normally this Pm I'll denote the mechanical power. So it is better to write the Pmax. So it is a steady state stability limit. If we differentiate that Pij in the previous case here, if we differentiating this, that we have, if you are differentiating that, the Pij with reference to delta here, that is again here delta just I have written, it is nothing but the delta between the bus 1 and the bus 2 is your delta. So always you must be very much careful what is this delta. So if you are differentiating this, then the voltage here is a Vi Vj, and here your x, it is your cos delta. And this coefficient is called the stiffness of line, or it is called the synchronizing coefficient of the line. So this term gives your idea that what is the stiffness constant of the line. That is very, very important, how much your system is stable. Also in the classical approach, we made some few more assumptions, and that is basically the saliency of synchronous machines are neglected, and resistance of lines are also neglected. In the classical approach, as I said, your two type of machines may be there. Here it is a stator, and here is your rotor which is rotating. So if it is there is a constant air gap, then it is called wound rotor, and if we are having some poles and we have the different air gap that is rotating in the machine here, so here we have the different air gap, here we have different air gap, and this is called the salience machine, and this is called the saliency of machine. So we can ignore, means here we can write this xd prime will equal to xd, then we have to ignore the saliency. We assume that both quantities are very close, but normally it is not so, it is very different. And also the resistances of the lines, it is not only lines, even though of the transformer we have to ignore, and the resistance of your synchronous machine is also ignored. Now let us see the single machine infinite bus, this SMIB, the single machine infinite bus system, where again the previous case we use here a generator G. This is your machine is represented by its equivalent impedance, that is nothing but your JXD or XD prime. Here we have to take the subsynchronous transient reactance, and this machine is the internal here E prime, that is equal to the magnitude. This is a complex quantity, so the magnitude angle delta with the reference to the infinite bus. So the infinite bus basically denoted by it has the infinite inertia, system inertia, whole this system basically, this is a system where this bus is there, so it has the infinite inertia, it has the constant frequency, and it has a constant voltage. So these three criteria basically gives you the criteria for the infinite bus. And the voltage here, as I said, the voltage is the V infinity, here I have written angle 0, and then with the reference to this angle we have taken this angle delta. This is your transformer, this is your terminal voltage of generator, this is another bus where this is a line is there and it has some impedance. Now this machine here is nothing but a spring mass system. Here there is some inductance is of K. The total this we can denote whole this machine. This is your infinite bus where this V infinite angle 0, and this is another mass. So this is just like a mass spring system, and then it will have some, and then we can analyze the dynamics of this system. As you know, the dynamics of this system can be written and we can solve the differential equation. Now there is a two type of concept. If there is a three-phase fault, let's suppose at this bus as is shown here. If there will be three-phase fault, there will be this machine delta will be changing. Why? This electrical power, due to this fault, more power will be flown. As I said, the power here is your nothing but your E prime V, that is infinite, the total X, completely X, sine delta. What will happen now? This is in steady state and this PM is almost constant. We have assumed this. Now this three-phase fault is there. What will happen? This X will be changed and this X will be reduced. So means more power is flowing. So your PM is not equal to PE during this three-phase fault. So this, to make it, what will happen? This PE, this delta will keep on increasing. Because this value is larger, if it is to maintain this PE constant, this delta, you can say delta will increase, and now you can say delta is increasing. So over the time period during the fault, this delta again can follow the different trajectory. One condition you can see, if delta is following like this, and finally it is stable, no doubt there is a possibility at this point, this fault is clear. If the fault is persisting and its fault is not severe, so delta will increase and then it will be stable. But if this fault is cleared, so then delta again may come to this its initial value, maybe. Again depends upon the whether fault is removed or not. If fault is removed, then it may come to its original value and the system is called to be stable. But this delta can increase like this till this fault is again clear, the system is, the delta is keep on increasing and it is losing the stability, because here if you will see, if this is your delta and this delta is keep on increasing, then system is unstable, and system is unstable, then it is called there is a loss of synchronism. So it is losing the synchronism operation and then we can say system is unstable. To see the system modeling, again this whole the rotating mass, here it has some inertia constant. This rotating mass we have the synchronous generators. The systems also we are having some damping. Damping means we have some resistances, means there is some damping effect as well, and let us it is a D, and here this your Tm, this mechanical torque, that is the mechanical power divided by this nominal frequency, that is omega naught, and this omega naught is nothing but it is equal to your 2 pi f naught, and f naught is your synchronous frequency. This synchronous frequency is decided, as I said, it is 120 f upon p. That is how much you are rotating. This rotating speed, this is giving a frequency based on the rotation, so number of poles of machine. So this is a rotating mass, and again the two forces, one is the Tm, another is your Te. So your electrical power which is coming through this one going that side, it is electrical power, and the input we are giving in terms of mechanical power. So at the balance, as I said here, again this T must be equal to your Tm, or we can say this P will be equal to your Pm. Means your electrical power will be equal to your mechanical power, and then it is called steady state. But during the disturbance it may not be equal, it will try to equalize this T. As I said, the Pm we have assumed constant in this transient stability analysis. So only parameter which is changing your Pe. So the various here in this system modeling that will be used, this Pe is in per unit electrical power output, that is the power which is coming out. Pm is mechanical power input, the T is the electrical torque, Tm is mechanical torque input again, delta is the rotor angle, and this angle is the angle between the two, here your reference axis and your here rotor axis. So this is the angle between the reference where you are measuring all these angles, and this is the angle between your, and this is called your torque angle or load angle. angle between the two axes here. Your h is your inertia constant of the machine, whole system basically. Here we are talking, if all machines are coming into one combined machine, then it is inertia constant of complete system, or if you are analyzing one machine with the infinite system, then it is the inertia constant of one machine. So D is your damping coefficient, as I said. Here this V infinite is your infinite here voltage. This is a terminal of this generator. This is the X prime, that is a transient reactance of synchronous machine, and here is E is the behind the transient reactance. So the whatever the power that is here is coming out, again this will be equal to your PM in the steady state. This XL, this include the transformer and the line reactances. As I said, we had one transformer and then we had the two lines, again the same example, and here it was EF. So this is your XT and plus XL1 parallel to XT2 parallel. So it is X is the combined of the transformer as well as the two transmission lines, those are in parallel. So for the transient analysis, normally we use the swing equation. Let us see what is the swing equation. Under the normal operating condition, the relative position of rotor axis and the resultant magnetic field axis is fixed. So the rotating axis of the rotor and the magnetic field axis is fixed. The angle between these two is known as the power angle or torque angle. During any disturbance, rotor will accelerate or decelerate. Thereby what will happen, there will be change in the rotor angle. So with the acceleration and the deceleration with respect to the synchronizing rotor air gap MMF, and relative motions begin basically. The equation describing this relative motion is known as swing equation. Means during any disturbance, rotor will decelerate or accelerate, again depending upon the PM and TM balance, means whether the TM is more, means input is more than the electrical output, then machine will accelerate. If your input is less than your output, then it will be decelerate. Then accelerate with the respect to the synchronizing rotating air gap MF, and a relative motion begins, and the equation describing this relative motion is known as swing equation. If after this oscillatory period the rotor locks back into the synchronous speed, the generator will maintain its stability. If the disturbance does not involve any net change in power, the rotor returns to its original position. If the disturbance is created by a change in generation, load or network conditions or network topology, the rotor comes to a new operating angle relative to the synchronously revolving field. Swing equation can be expressed in terms of the second order nonlinear differential equation as here h over pi f naught derivative second derivative of delta with respect to time, that will be equal to Pm minus P delta, and that is a function of your delta minus this damping constant, and then we have d delta upon dt. Basically this d delta upon dt is nothing but your change in speed. So if we neglect this term, this PD, the damping effect, as I said in the classical analysis we always neglect this. So this can be neglected. So we will have the equation here like this. Now you can see earlier I was using this H and now I am using M. So this M and H, they are defined, they are related as this M is angular momentum is equal to H upon pi f naught, and this omega is nothing but this delta upon dt. So whole this equation can be replaced and can be written in terms of omega. So this M is angular momentum, and that is defined as inertia I of whole system multiplied by angular speed, and its unit is your megajoule second per electrical radian or degree. I is your moment of inertia. Here the delta is your theta minus omega naught t, and theta is angular displacement of rotor, and omega naught is the speed of the synchronous rotating frame. Now let us again, I use this H and how we have to get the information of this H. Now let us define the per unit inertia constant H, that is H is defined as the stored kinetic energy in megajoule divided by the MVA rating of the machine. If you will see the unit of this, is the unit is nothing doubt here, the unit of the kinetic energy is megajoule, so I can write here megajoule and over your MVA. So this is your power, this is energy, and you know the energy here, it is nothing but I can say MWH. So here the total, this is nothing but your second. So unit here the megajoule per MVA, or it is second, and H is very widely used because H gives to what is the inertia constant, and this kinetic energy stored, it is nothing but I can write here half I omega square, this Ke, and this will be equal to I can write half I omega into omega, and this is nothing but your and here I can say half m omega, and this is nothing but your G, and G is your rating or installed capacity of your synchronous machine. So knowing this m, knowing your G and omega, that is a synchronous speed, we can get the H, or knowing H we can get m, vice versa. So the sync equation can be written as in terms of H, it is again if you are using delta in electrical degrees, then it is 180 F here, double differentiation of delta with respect to time, and here your power minus this mechanical power minus your electrical power in per unit. So here we are just talking about the per unit, it is divided by the base unit, so it is per unit always because this is in H in per unit. This unit at all it is per unit, so it is not in megawatt. You have to write the base what you have used, and base is of course is a MVA rating of machine. So simply we have divided here. So if you are using the delta in electrical radians, then here it is a pi f, and then we can write this one. Now the various type of machines are used, synchronous machines I am talking, and then the inertia constant is the different for the different type of machine, and this inertia constant H here it is basically 3 to 10 seconds for the steam turbine generating system, it is from 2 to 4 for a hydro generator system. Normally if H is large, then we say this machine is large, if it is small, then machine is small. You can see the induction motor, this inertia constant is 0.5 second, means its size is very small. So this inertia constant gives information about the size of machine. Why this steam turbine generator system is having high inertia? Because you know here we have this generator, that generator is coupled with the various type of turbines, different stages of turbines. So they are also very high speed and rotating mass are there, so the total H of the system is more compared to the hydro, where one the hydro turbines are there and then it is coupled with your turbine system here. So it has a lesser time constant, H means inertia constant. So it is 2 to 4 seconds. However, the steam turbine again depending on the size, if it is very large then it is actually very high, and if it is small then it is again small. Again in terms of synchronous motors, because we can use the synchronous motors as well. So the average value of H it may be 2 seconds. Synchronous condensers, if it is large then it is maybe average value is 1.25, and if it is small then it is 1. What is the synchronous condenser? To understand here, the synchronous condenser are nothing but they are some sort of alternators, but mechanical power output, this electrical power output is 0. Means if you are using here this generator and there is no here PE is 0, you are rotating to provide the reactive power only Q, then it is known as synchronous condenser. So you can either generate or absorb reactive power by this synchronous alternator. We know that by changing the excitation system, we can generate or we can absorb the reactive power. So it is acting as a some variable capacitor along with the inductor. See, one zone it is giving, another it is also absorbing. So it can do, and we are not taking any real power load, then it is called synchronous condenser. Now let us see the physical interpretation of the swing equation that is here. Means we can derive this swing equation in terms of change in the speed with respect to time, the derivative of speed with respect to time, this m value, this Pm minus P, and that P is a function of delta. Again, this P is nothing but your P, that is approximate the V1 V2 upon x sin delta. Normally these voltages are constant, we assume that's constant, so it is a function of sin delta and it is a nonlinear function. So this differential equation is a nonlinear differential equation. So here it is your rotor, and rotor is rotated by the mechanical input, and then we are taking the electrical output, and this machine is rotating with the speed of omega. Now if this Pm is equal to P, what will happen? This component will be equal to 0. Means if Pm is equal to P, then this component here m d omega upon dt will be 0, and this shows that d omega upon dt is 0, means your synchronous speed, this machine is running at the synchronous speed, neither it is accelerating nor it is a decelerating. So it is a steady state operation. Let us take if mechanical power is more, means here this is more than this output. What will happen? This machine will rotate and accelerate. Why it is so? Because always we know this energy is conserved. When this power is coming here, it is going less, so that power will be stored in this here machine itself. And how alternating, or you can say rotating mass will store the energy, and that is no doubt in terms of kinetic energy. Means that energy will be stored in the kinetic energy, so the kinetic energy will increase, therefore the speed of this machine will increase. So this is the same concept. So if Pm is more than P, then this component will be more than 0. What does it mean? Your rate of change of speed is more, means your this omega will be now more than your synchronous speed, and then this rotor will accelerate, or you can say it will be speeding up. The reverse is also true. Means if your mechanical power is less than electrical power, means you are taking more power than your input. What will happen? The energy which is here in this mass will be taken out, and then means kinetic energy will be reducing, therefore the speed of this system will be reducing, and then we can say this change in the omega with respect to t will be less than 0, or the rotating here speed will be less than its nominal, or you can say speed of the synchronous speed of the system, and the rotor will decelerate, or it will be slowing down. So the swing equation for the two coherent machine. So far we have used H, here it is H, Rm, whatever you are talking about. So if it is one machine here, and then it is connected with your infinite bus here. Now if there are two machines, means here you are having two machines, and then you want to include and combine together, then we can say that two coherent machines can be combined, and their inertia constant can be also added together. So here it is your Pm1, another machine here it is your Pm2, and this is another here, this is synchronous machine. So if we are having two coherent machines, like here machine 1, I can say G1, here it is your G2, and it is connected by its equivalent here internal impedance, here again internal of this machine, and this is your infinite bus, means that the voltage and angle is constant. So these two machines can be combined together, and then again we can basically with this we can write a single machine here with the sum here equivalent, and this machine is like this. So here this is your now this Pm equivalent, and again the electrical power which is going the P equivalent here, so I can say P12 here, Pm12 I can write. So we can represent these two machines here like this one. If both are in the coherent, means they are oscillating and rotating in the same speed. So if the inertia constant here, this H1 here here is S2, and the electrical power which is feeding is P1, and here is PE2. Then we can write this H12 will be nothing but H1S2 over H1 plus S2. We can have this one expression for here, and this your PM12 is can be related as the PM1S2 minus PM2 is PM2 here multiplied by this H1. So this is the PM1 multiplied by H2 minus PM2 multiplied by H1 divided by H1 plus S2. Similarly, the PE12, this combined here, will be the PE1 here multiplied by this S2 minus here PE2 multiplied by H1 and then divided by here, and the angle here, if this is the angle E1 angle delta 1, here this is the E angle delta 2. So the angle here, the difference will be your delta 1 minus delta 2 with reference to 0, and then we can go for the equivalent. So this is again why we are going for this. If you are having two machines, then you can again go for this is nothing but your single machine infinite bus system, SMIB, and then you can go for the classical approach and then you can analyze it. So for analysis of the transient stability for this single machine infinite bus system, we can use the equal area criteria, and that is very popularly used. So the equal area criteria is a quick prediction of stability. It is very quickly you can analyze whether your system is stable or not following the fault. This method is based on the graphical interpretation of the energy stored in the rotating mass as an aid to determine if the system machine maintains its stability after a disturbance. The method is only applicable to one machine system connected to an infinite bus or two machine system. Means if the two machines here, basically what is one machine infinite bus system, you can see again the same example which I explained earlier one. Here one generating system here we have the infinite bus, means this is also a machine which have the high inertia, means large inertia, infinite inertia, and where the voltage and the frequency are the constant. So it is only applicable for the two machine system, means this is two machines, or other words you can say it is the single machine infinite bus system. So it is only limited to that. It is not possible to go for the multi-machine system. If the machines are several and connected by the different transmission lines, then we have to go for another analysis. We have to solve the equations, the nonlinear equations, by help of several differential equation solution methods. So the swing equation here, as again I can write here, that is written by this one. And this PM minus PE is nothing but it is a PA, it is called the accelerating power. So whether PA is 0 or it is positive or negative, it decides whether your machine is accelerating, your machine is decelerating, or it is in steady state operation. So this equation, now you can see this equation can be written as in this form. Means here from this equation you can see I can write this d omega over dt is some constant integration of PM minus P angle here delta. We can derive this equation, no doubt, very easily. We have to write the two differential equation, and finally, or you can say if you can differentiate this equation here, you will find this equation without any problem. So this equation gives a relative speed. What is this? This is your relative speed of the machine with respect to the synchronously revolving frame reference. For the stability, this speed must be 0 at the some time after this disturbance. Therefore, we have for the stability criteria this must be 0, means we can have this delta from delta naught where it was operating to the delta. If we are integrating for that period, then it will be the 0. To understand this, it is very easy. Let us consider sudden increase in the power input. Means here this is your system, this is infinite bus, where we have suddenly, earlier it was operating at the PM0, and then we have increased this PM1. Suddenly we have increased the power input. Consider the machine operating at the equilibrium point delta naught. What is the delta naught? You can see here, this is your delta naught. This is your delta variation. This is your PE. This is nothing but your P delta curve of the combined composite system, including your here this infinite bus, here another terminal, here your generating terminal, here your generator, and this is your transformer, included everything. So it is operating here, as I said, here it is operating because your mechanical power PM0 is this axis. So the operating point will be your A, where it is intersection of this P delta curve with this your PM0 curve, that is a constant. So it is a constant we have assumed. So this delta naught is your initial operating angle, and corresponding to this mechanical power PM0 that will be at that point will be equal to your P0. Means your electrical power is equal to your mechanical power in the steady state, as shown in that figure. Consider a sudden step. Sudden step here, you can see that suddenly it is increased here to PM1. Now what will happen? Now it's stable, this is a PM, so your B point is the post increased stable point, this B point, because at that point here this PM1 will be equal to your P, now it is, I can say, delta 1, where it is equal. So at the initial it was a PM0, it was your equal to the P delta naught. So this B point is your another post increased power stable. But means, so just we have seen the sudden change. Since PM1 is greater than PE1, the oscillating power on the rotor is positive because you have increased the PM. Means your at that point your P was P0. So once you are increasing, your machine will accelerate, because if PM is more than P, as in previous slides I showed you, that it will be increasing and it will be accelerating. So your power delta, angle delta will increase. Means here your this delta here it will be increasing like this. So it is increasing. The excess energy stored in the rotor during the initial acceleration is here area A1, that is area ABCD. Means here you will see, here this area, this energy is, that is A, B, C, and that area is, you can say area A1 is the stored energy of this machine, that is ABC, and it is basically integration of delta naught to delta 1. Means here is a delta naught, means this curve minus this curve. If you are integrating from here to here, means your this area A1 will be nothing but integrating from 0 naught here to delta 1. Here this is a constant curve, so this is your PM1 minus this curve, that is a P, and again it is a delta. So this area is just, this area here it is written as this one. With increase in the delta, the electrical power will increase, and when this delta is equal to delta 1, the electrical power of machine matches the new power, that is a PM1, even though the oscillating power is 0 at this point, the rotor is running above the synchronous speed. Hence delta and the electrical power E will continue to increase, and now this PM will be less than P, and causing the rotor to decelerate toward the synchronous speed until again this delta is delta max. As a result, the rotor must swing past point B until an equal amount of energy is given up by the rotating mass. The energy given up by the rotor as it is. Now what happens? Now this from here it has to go here, and your rotor is now accelerating. Once it is accelerating here, it has reached. but your rotor is oscillating at this point B, it is satisfied this. But it is machine you are oscillating, so what will happen? It will try to de-oscillate and it may go up to this point D. And here again, now speed of the machine will be the synchronous speed. Here it was the synchronous speed, it started oscillating due to this mechanical power is more, and it is here it saw that the PM is P, then it will be retarding, but the delta will be keep on increasing and it will be reaching up to D, and again it will be at this point it will see that your PE is more than PM1, so it will again retard it back. So this is basically it will be oscillating, it will be going back, and the system damping will try to stabilize at certain point B. So the de-oscillation here back to the synchronous here area A2, that is area BDE, will be nothing but the integration from delta 1 to delta max. Here at this delta max, what is happening? The machine is not oscillating. Machine speed it is rotating at the synchronous speed, but the electrical power is more. So it is integration between this and this. So it is a P minus PM1. It is this curve minus this curve. If you are integrating from here to here, this delta 1, this delta 1 to delta max, that is a PE minus PM1. If you are integrating with the delta, then you can see the total. The resultant is the rotor swing is to point B, the angle delta max, at which point you can add these two areas, that is a delta 2 to delta 1, that is a PM1 minus PE delta, the previous area, plus here from this area, if you are means from the previous equation here basically, from this equation, if you can write this equation in the here, means it is from 0 to 0 naught to 0 1 PM1 minus E, here again delta 1 to delta max, here the same equation. What is happening? Now you can see this is nothing but your minus area 1. So I can write this is nothing but area A1 minus area 2 is equal to 0. This is the area which we have written. So now what is happening? From here we can say the area 1 is equal to area 2, and this is the case of the stability. If the system is stable, that must be satisfied. So if the area here, that is a oscillating energy, kinetic energy here, and is equal to area 2, then it is known as system is stable if area 1 is equal to area 2, and this is known as equal area criteria. The rotor angle would then oscillate back and forth between angle here. So basically your rotor will be oscillating between these 2 points. It is not going beyond that range. It is here again less than this. And its natural frequency. The damping present in the machine will cause these oscillations to subside, and the new steady state operation would be established at the point B after certain time. So this machine is here basically, if you see, it is oscillating your delta here, from here it is oscillating, and finally it is at the new delta 1 it will be stabilized. So if you are plotting with the respect to time, what will happen here? This is, let's suppose, your time, this is delta, means your machine here operating initially at delta naught when the disturbance has taken up, means just you have increased the sudden input of the generating system. What will happen? It will be here oscillating, and finally it will be steady state at the lambda naught, delta naught. So this is basically, and this damping is to the system damping, because there is some damping in the system and it will be stabilized and system will be stable. But there is a possibility if there is again excessive change. This point D has gone beyond this, then machine will not come back, and then it is said the system is unstable. So in this lecture we saw that transient stability analysis using the classical approach. We made certain assumptions, but it is very advantageous if you can form the single machine infinite bus system, and then you can see the behavior of that machine with reference to certain fault in the system. It is quickly giving the idea whether your system is stable or not without integrating the system, means without solving the differential equation here with the help of the two areas, we can know that whether system is stable or not. In this case, we saw that area 1 here is equal to your area 2 for the stable system. But if this area is more than your area 2, the system is again this area, kinetic area, this inner area basically always gives information that whether you are at the verge of stability or whether your system is very strong in the sense of stability. So this equal area criteria is used to know that whether how much you can load your system. For example, in this case, you can see your system is operating here. Now it is always advantageous to know that how much you can load in the system. Means in this case it is the PM1. There is a possibility you can go up to the PM2. Here it is your PM2, this point, and then if there is a sudden change here, what happen? Your system may go somewhere here, and then you are somewhere angle here. So what will happen? Now this area is the different area than what you have area here. So with the help of, we can know what is the maximum loading that suddenly we can put on the generator without losing the stability of the system. And this classical approach, as I said, it is limited to the single machine infinite bus or the two machines here. This is another machine and here it is another machine. Then we can analyze and then we can know using your equal area, means here area 1, that is your energy storage here, that is accelerating. So energy that is you are giving, that is increase, that energy is basically in terms of accelerating, and here is a decelerating. So in this lecture we have seen that I have taken only one case when there is a sudden change in the input to the power. In the next lecture we will see that how much we can load, and at the same time we can also see if there will be any fault in the system here. There may be some fault here at this line at this end, and if it is tripped out, then again whole your reactance, the topology of the system is changed. There may be possibility due to this fault, this circuit breaker is tripped, and then we will see what will happen during the fault, what will happen after the fault, and what will be the system stability criteria. We can also determine what will be the critical clearing angle, means at what time you have to clear your fault, otherwise your system will be unstable. And then we will see with the help of equal area criteria you can determine your critical clearing time. Normally it is called CCT. So to know the stability of system, one approach here is the CCT, means how much you have what is your critical clearing time. This also gives the stability measures. At the same time, another approach is used, that is called energy margin functions, how much energy margin you have, and that is also used to assess the system stability in event of the transient faults, transient disturbances, or you can say large disturbances, and for that we have to analyze your transient stability analysis. Thank you.